Should I wait for like 2 minutes, Emanuela, or I should start?
Yes, no, let's wait maybe for 2 more minutes.
Okay. So, Emmanuel, can I start now? Or I should
Yes,
wait a
we have
bit?
about half the participants, but I think,
Oh,
I mean, if it's being
okay.
recorded, yeah, but if it's being recorded, I think let's start.
Should we start like 8:10, 10 past 8?
No, I would suggest we go ahead. It's being recorded.
Okay.
So let's not make colleagues wait.
Okay.
Let's go ahead. Yeah.
Okay. Good morning, everyone. My name is Lare Adeola. Today, I'll be taking lecture 3, Applied Machine Learning Applications, a brief introduction and guide for use in trade and supply chain. So here is the lecture outline. There was a bit of a switch in the lecture outline because I'm not a supply chain expert. I'm an applied machine learning expert. So what this lecture is going to be about is teaching you the process of applied machine learning. Then as all of you are experts in your own field, you can now apply the AI or ML model to any task at work. What is applied machine learning? Applied machine learning can be loosely defined as the discipline of using theoretical concepts in machine learning and finding an application or use for them in any field or endeavor. This means that we can apply machine learning to a diverse array of fields ranging from healthcare to astronomy to the creative arts and even to this modular course, trade and supply chain. There are different aspects of applied machine learning.
I think someone could you please mute your microphone if you're a participant? Thanks.
The different aspects of applied machine learning. Here I've listed 8. The first one is the problem definition. The next aspect is the task classification. The next one is the data preparation. The next one is the model selection. Then we have model training, evaluation, deployment, and monitoring and maintenance. For this lecture, I'll be taking the first 4. The 5th and the 6th may be taken by the next lecture in predictive modeling. Foundations of applied machine learning. Applied ML is unique from industry to industry. It is founded on 2 main knowledge, theoretical knowledge and domain knowledge. Theoretical knowledge involves having an understanding and technical know-how of the various algorithms and data processes involved in building machine learning models. It is the toolkit, the spanner, and the screwdriver of the applied machine learning field. Domain knowledge involves having specific expertise or relying on such specific expertise when solving real-world problems. For example, a biochemical engineer will have domain knowledge in building a machine learning model that can detect pressure in joints for applications in physiotherapy or biomechanics. A supply and logistics chain professional will have domain knowledge in using machine learning to detect the best optimization routes. Machine learning task classifications. There are two major machine learning task classifications. This was mentioned in the last lecture. We have the regression task and we have the classification task. And here now, there are two examples. I'm saying which box contains examples of classification outputs and which one represents regression outputs. The first box is say 50% reduction in overheads, 1.67% growth rate, 13% inflation rate, $4 million profits, and exchange rate of $1 to 75 cents. The next box is car, you have diabetes, you do not have glaucoma, you're suffering from too much happiness, she's a girl, a great song. So who here can tell me which box is a classification, contains classification tax, and which one contains regression tax? Yes, Anna?
First is regression and second is classification.
Yes, correct. Thank you, Anna. This is the regression box, and this is the classification box, as Anna said. Regression tasks usually involve numerical variables, e.g. your age, inflation rates, exchange rate, profits, measurements, distance covered, etc. Classification tasks usually involve categorical variables, e.g. gender, names of animate and inanimate things, booleans, true or false, values, medical diagnosis, etc. It is important that when framing a problem to think of the machine learning task classification. What kind of tax is this? On the x-axis, we have what level. On the y-axis, we have salaries. And this on the x-axis is levels of experience, years of experience. So we can see that when your years of experience is 2, your salary is around this. If it's 4, what is showing is, what this chart is showing a trend that the more your years of experience, the higher your salary. So this is a regression task. This is also another regression task using the upper confidence bound algorithm. This is used in reinforcement learning. So this is showing on the x-axis we have the interaction count, and on the y-axis we have the interaction count, and on the x-axis we have the adverts. So what this is showing is each advert, how much does it convert? How much people see each advert? That is what this task is showing. And yeah, this is also an example of a regression task.
So sorry, Larry, there's a question for you from
yes.
Yes.
Thank you. Good morning.
Good morning.
Sorry, I'm a bit confused. What you're showing us now are variables where if we had this task, we should know what type of machine learning we should be looking at. Is that what we're trying to cover?
Yes.
Okay.
This is also another example of a regression task. Here we have the turnout percentage on the x-axis and we have the states on the y-axis. So what this chart is showing us is the least political active states in a particular election. And this is another example of a regression task. This is very simple to know. You can see like the last, usually when you get a data set and when you have a table, as you will see in the next lecture in predictive modeling, usually the column, one of the most important columns, or the dependent variable column, is usually the last column, as you can see here, price per watch. And you can see, as we said earlier, all these are numerical variables. And here, this is different. This is a classification task. What this is showing is are the different variables that affect diabetes. So here we have different risk levels, 0, 1, and 2. Showing the different if one has type 2 diabetes or not, or one is just normal. And here we can see that based on what this is showing are the different correlations between one variable and another. This, because of the risk level, what we're trying to classify is if a patient, based on some attributes, has sorry, this is not diabetes, this is maternal. This is the data on maternity health. So what we're saying is that based on a series of inputs, does this patient have is this patient in an high risk of maternity health or not?
Larry, there's another question for you.
Okay. Yes, Anna.
Can you go back to the slide on maternity health?
Yes.
So this is probably preeclampsia risk or something like it. So it's about the task, right? Because
Yes.
you want the risk level as an answer. But if you wanted to predict, for example, the curves, then it would be a regression task.
What? How do you mean, Anna?
Like, for example, if you had like you have the always 3 patients, right? The blue one, the green one, and the red one. And if you had some data and you want to predict the curve going forward, like let's say you have the data until month 3 of the pregnancy and you want to predict month 9 of the pregnancy, then it would be a regression,
yes, a regression task. Yes,
but
yes.
because you have a data set that's complete
Yes.
and you just want, is she at risk or is she not?
Yeah.
It is a
classification tax.
classification.
Yes, yes.
Okay.
And Anna makes a very good point, because to be honest, in applied ML, you can craft a classification tax as a regression tax, and you can also craft a regression tax as a classification tax. I'll still be talking about that later in this lecture. So good contribution there, Anna. And here, this is another example of a classification tax. This is a word cloud. So this is used for sentiment analysis. We want to know, given a particular data set, what are the sentiments in that data set? Is it positive? Is it negative? Is it neutral? So this is a classification tax, and this is using a branch of machine learning called natural language processing. And this is another classification tax. Here, this is computer vision. This is the field of computer vision. And here you can see we're trying to detect, what this is trying to do is to detect unsafe driving habits. That was what this research was about. And here we're trying to give in a series of data based on images. We want to know if the person is sleeping or drunk, or the driver is alert. So how do we craft an applied machine learning tax? We said there are 5 ways, 5 steps involved. The first step is problem definition. The next step is tax classification. The third one is data conundrum. The fourth one is the machine learning algorithm. And the fifth one is the results inference and deployment. Problem definition. This involves defining what problem you want to solve, and also deciding if machine learning or artificial intelligence is the effective and efficient solution. The images below show different problems which artificial intelligence can help solve. In this paragraph, what this means is that machine learning is not a do-it-all. You understand? You know, they always say that you don't solve every problem. Like you don't use every hammer to hit a nail to solve every problem. So there are some problems you may encounter at work, and machine learning or AI may not be the best solution. A solution could be maybe something like fuzzy logic or rule-based, depending on the scenario. But there are situations whereby machine learning is very good. And here we're looking at some of them. Like the first chart is showing falling profits. The one in the middle is showing predicting overhead costs. The third one is predicting malaria deaths. So basically, AI attacks are best handled in scenarios where there is a deluge of data. When there is a lot of data, that is the first step. If there is no data, it's going to be difficult. Although now there's a lot of research going into synthetic data, but at the initial phase, if there is no data, it's going to be difficult to be able to craft a machine learning task for it. Then tax classification. Here you determine if the problem is a regression tax or a classification tax. Sometimes the type of data, unstructured, for example, will automatically lend itself to a particular task classification. Examples are natural language processing problems.
Lare, do you have examples of this thing that they can run and you can run and they see it?
They'll see it later, Prof. There's an outline. Yes, I'm getting there.
Okay, very good. Because it's very important. Like you are showing them this, I want them to see how it can actually generate that, and then they can test it later on. They may not have time to test it themselves now, but they will do that later on. All right, continue.
They'll see it. There's a part for data engineering. And examples are natural language processing problems and image/computer vision tax. And here we can see an image of a computer vision tax for it. And here, for this, you will know that this is a classification problem and not a regression problem. Data conundrum. What type of data is available? How will I get the data? Is it structured or unstructured? So structured data is data that is neatly organized into rows and columns, like all these tables or data that you see in Excel spreadsheets. Then unstructured data is the opposite of that, basically. Unstructured data is in different domains from media data. So we have things like images, text, audio, all that are unstructured data. So we said personal, does the data contain PII, personal identifiable information, privacy concerns, ethics, etc. Data is a serious conundrum. And here we can see different legal issues regarding data, but Dr. Ike during his lecture will talk about that. Machine learning algorithm. There are various machine learning algorithms for different tasks. Each of these algorithms have their unique underlying principles. E.g., some are stochastic, which is random. Some are deterministic. Some we have trees. We have probabilistic. We have ensemble, which is using different algorithms together. Ensemble is gotten from the French word which means together. Modeled after, there's some that are modeled after the human brain, such as neural networks. There are a few popular algorithms, as was mentioned in the last lecture. We have the linear regression, logistic regression, naive Bayes, KNN, decision trees, random forest, gradient boost, support vector machines, neural networks. There are a lot of algorithms. And here on the right-hand side, we can see a particular machine learning problem. This is a clustering algorithm. So this falls under unsupervised algorithms. Results, inference, and deployment. At this stage, we intend to analyze the model we have built to make sure it's fit for purpose in the real world. It is important that any machine learning model we choose in the previous step intuitively is reliable and to a subjective degree can solve the problem definition. Depending on the task classification and especially the domain, different metrics are used to analyze the results of our models. This is why in machine learning, we tend to separate the training data from the test data. So already in the last lecture, Dr. Pradeep spoke about metrics. And yes, that is very true. We use different metrics to be able to test different machine learning models. Some metrics include something like MSE, mean squared error. We have accuracy. We have F1 ratio, different metrics for different purposes. Now, our first case study, salary versus years of experience. Remember the 5 steps? First one is the problem definition, the task classification, the data, the machine learning algorithm, the results, inference, and deployment. Now, what is the problem definition? We want to find out the relationship between salary and years of experience. Is it direct or inverse correlation? How many years of experience do I need to have to earn a certain amount of money? And here we can see some snapshots of the data from the beginning of the data to the end. We have the head and the tail of the data. And here by the the right-hand side, we can see the correlation between the two of them. And we can see that there's a high correlation between years of experience and salary. The task classification. When doing task classification, we have to define what the dependent variable is and what the independent variables is or are. In this case, salary is a function of years of experience. Mathematically, we can define this as y is equals to f of x, where y is the salary and x is the years of experience. In this example, we have just one independent variable. And here, the independent variable is years of experience. But this is not always so in real life scenarios. It is much more common to have 10 or more independent variables depending on the complexity and nature of the problem. Since the salary variable is numerical, this is a regression task. And I said here that it is also possible, as Anna has noted earlier, to frame regression tasks as classification tasks. For example, we could be interested in 2 salary thresholds above 100,000 and below 100,000. So that now becomes a classification task. The data conundrum. We have data for 2 variables. We have salary and years of experience. The salary variables data is numerical and they are integers, though pandas has converted them to floats, while the years of experience variable are floats. We'll still come back to pandas later in the practical session, e.g. 1.1, 1.3, etc., which can be translated as 1 year, 1 month, 1 year, 3 months, etc. The data length is 30, so this data records for 30 different professionals. And here, this is a snapshot of the different, the important attributes about the data. So we have the count, that is the length of the data. We have the mean for each column, each of the data, both the independent and independent variable. We have the standard deviation, that's what STD stands for. We have the minimum, that is the lowest value in the column. Then we have the 25% percentile, 50% percentile, 75% percentile, and we have the maximum values. The line plot by the right provides a visual summary of the data. It is always important that when you have data, you try to plot it. You want to understand the trends available in the data. Here we can see the trend in the relationship between salary and years of experience. The more the years of experience, the higher the salary. So now that we have the data, we have a problem definition, we have the task classification, we know that we're going to, this is a regression task, we have the data. So which algorithm are we going to use? I mentioned so many. How do I select the right algorithm? Where do I start from? I said for this case study, we will be using the simple linear regression for two reasons. Number one is that we can already see from the line plots that there's a positive linear relationship between the two variables. This algorithm is simple and lightweight to run, and our data set size is small, and there's no need to use a complex algorithm out of the box. It is best to start with simple algorithms, then progressively change them if the metrics you choose are poor. So what I'm trying to say here is that we have a data set. We have the dependent variable, we have the independent variable. We have the length of the data set. We have the length. Yes, we have the length of the data set, which is 30. We have already seen the trend in the data set. We have seen that there's a positive relationship between salary and years of experience. And now what we now say is that, okay, let me start with the simple, because it is advisable to always start with the simple algorithms first, then progressively get to the more complex ones. And I said, okay, let's start with the linear regression. And you must remember that a linear regression seeks to fit a line of best fit to the data points. It has a constant and a coefficient, and it can be written as y is equals to a of bx.
Somebody's hand is up.
Okay.
Thank you. Thanks again. Just for clarity, is it expected that we will be using these algorithms to run an LLM? Because maybe then I'm confused. I thought it's more learning how how AI is used, in supply chains. But is this, sorry, because you're covering this, are we expected to? Is this part of what we're expected to do, to be able to actually design machine learning?
Yes. So what this lecture is about is how to apply machine learning to any different task. So I'm teaching everyone how to apply machine learning. Then depending on your task in your role at the WTO, you can now use it to all this knowledge. You can use it to apply to whatever problem you have at the office.
I think the important thing also is that other people that will be teaching, because today is just more on applied knowledge of what AI can do. As we go on, there are people who will teach you supply chain, who will break it down, into what is needed. But today we just want to give you everything on AI, what AI can do in applications, so you can see different areas. So that's why it's more like a lab class today, teaching general. You understand?
Okay, so thanks.
All right.
Yes,
somebody
there's another
said
question.
Hand is up.
Yeah.
I think Anna, you want to ask first? I think you raise your hand.
We saw your hand up.
Raise your hand.
Yeah. So my question is, for this kind of simple regressions, usually take the example of salary. We have like a year experience, but we have other variable from like a classifications task as well, like gender, whether you and the the culture where you come from, country you come from as well. Would it be like a combinations of both, like a regressions and classification tasks in one learning algorithm?
Okay, that's a very good question, Hank. So I think what you're trying to say is that each of the columns now are numerical. So we have salary that is a numerical variable and years of experience that is a numerical variable. But if we want to also look at gender, that is going to be a categorical variable. So we're going to have male, female, and binary, for instance. So how are we going to do that? So it's a very good question. In the next case study, we'll see more of those kind of variables, but let me just talk about it. So usually what we do, what they do in machine learning basically is that we transform the data in that scenario. So because the computer cannot understand text, you must turn that text into a numerical value. So in that scenario now, if we have male, female, and non-binary, so we can just turn them to 0, 1, and 2, 0, 1, and 2. So then they've now become numerical variables, and we'll now be able to continue with our regression task.
Pour les GCVK, par exemple, tu peux avoir,
Yes, in addition to the response received to the first question, I think the first question spoke to supply chain, how AI or machine learning applies to supply chain. I think the basic understanding here is that supply chain can be divided broadly into two categories: production and distribution. So all the activities that inform production, including data that informs production, the various variables that apply in terms of production, reaching that goal of producing an item, and then the distribution across various networks, and the features that apply within the distribution, including issues around taxes, projecting on taxes, projecting on the sourcing of raw materials into finished goods, all the allied features that play in here can become data that is available for the purpose of applied machine learning. I just provided that context so as to give some clarity. Thank you.
Okay, Natasha.
Thank you.
Yeah.
I think, forgive me if this is going to come up in the future sessions, but at the minute we're dealing with very fixed variables, very known variables. How is this going to work if there are assumptions and probably biases in some of the data that we don't normally understand? So for example, I don't know if we don't have evidence for political decisions or what direction it may go, or there's an assumption on the basis of a particular action that a member state or government can take. How can we factor that in, or will this come, if this is coming in a different session, then ignore my question and I can wait for it. But at the minute, all I'm seeing is the variables that we're talking about, they're fixed, they're very clear, they're very known, age and that sort of stuff. But sometimes we will be dealing with factors that have biases in there and are not very fixed or very clear. How do you deal with that?
Okay, so I think your question is divided into two. The first one is bias, you understand, bias on the data. And the second question is variables, whereby unknown variables, basically. Those are the two questions. In that, remember, when I started this lecture, I said it's not every task that you must use AI and ML to solve. Some problems, it may be philosophy that
yes,
you're going
exactly.
to use to solve. You understand? Yeah. Some problems, it may be ethics that you're going to use to solve. So AI and ML is not, that's why I said, it's not every, well, I don't know, I'm missing that proverb. It's not every nail you must use an hammer, or it's not every, I think it's not every problem that you use an hammer. I can't remember the proverb, but basically it's not a toolkit to solve all problems. Okay. You understand? So in the situation of unknown variables, you have to think, because now you're looking at politics. You understand? There's a lot of research in it. There's a lot of, but even with politics, so in politics, for instance, we can try to understand the sentiments. So you remember there was a slide where I was talking about the classification. I was looking at sentiments analysis. So sentiment is all about like the emotions. You understand? So in politics, you can understand, you can say, okay, I want to know what is the sentiment in this particular country at this particular time when they were doing this trade or when they were doing this policy or whatever.
Yes.
You understand?
Yes.
So it's not my domain. It is your domain as a policy analyst. You understand? So that's why I said domain knowledge is important. So when it's your domain now, you will understand that, okay, which toolkit am I going to use? You understand? I want to be able to model policy. That is no. I want to be able to model political, for example, political stability or political instability, which is an unknown variable. How am I going to do that? So it is from domain knowledge you can answer that kind of question. Then the next one of bias. So of recent, in the last maybe decade, there's something called explainable AI. So whereby explainable AI is basically okay, because a lot of times in AI and machine learning is almost like a black box, because we're putting in these variables and it's just spitting out the answer. You go on ChatGPT and it's spitting out the answer. But you want to understand that, okay, how did you arrive at this answer?
Yes.
So this branch is called explainable AI. Unfortunately, I'm not going to cover that. I'm sorry. It was not in the how will I put it? It was not in the domain that I was meant to cover. But explainable AI is a lecture on its own, because there are tools that we use. So there are tools like Lime. There's an algorithm called Lime. There's another algorithm called Sharp. So those are the tools that they use for explainable AI. So you will now understand that, okay, how did it come about this result? So there you're trying to investigate bias in the data.
Okay.
Yes.
Yes, as speaking to political questions, I think there's also, apart from the philosophical, the ethical explanation, I think technology has also tried to make some inroads into understanding semantics. That is the context underlying every piece of data. I think there's been research in the area of RAG. They call it RAG, retrieval augmentation generation, and all that, and all those complexities that sit within that. That is in itself not conclusive, but I must say that, yes, your question is quite appropriate. There are researches, there is a particular research in this area speaking to how machines can understand the semantics as well as the pragmatists that underpins specific data. But again, human instinct is still very relevant here. And I'll cover the ethics and the bias part of it in my intervention in lecture 9. Thank you very much.
Thank you. Thank you.
Yes, Anna. We can't hear you. Sorry.
You're muted, Anna. Yeah, you're muted, Anna.
Yeah, I think she has an issue with her mic.
Okay, that's all right.
Or maybe you could continue. She's frozen now, so I don't know whether she's disconnecting and reconnecting.
Okay.
But maybe you could continue and we can take her question later.
Okay. All right. So yes. So we're here. So I said remember the linear regression seeks to fit a line of best fit to the data points. It has a constant and a coefficient, and it can be written as y is equals to a of bx, where y is the dependent variable, in this instance salary, a is the constant or intercept, b is the slope or coefficient, and x is the independent variable, which is our years of experience. And here, at the end of the day, after running the model, these are the variables. We have the coefficient, the slope / intercept. Case study 2, diabetes diagnosis. Let's remember the 5 steps: problem definition, task classification, data, ML algorithm, then results, inference, and deployment. Here we want to build a model that, given certain attributes, can predict if one has diabetes or not. And here we can see the various inputs of the y variable. That is if the patient has diabetes or not. Type 2 diabetes. This data was based on type 2 diabetes from the PIMA Indian set. I would upload the data on Moodle later after this lecture. And here we can see this particular array, this particular data structure is made of two values only, zeros and ones. So 0 means is negative and 1 means is positive. So in this instance, 0 means does not have type 2 diabetes and 1 means has type 2 diabetes. So what this means is that this is a task classification. 0, you don't have symptoms. 1, you have symptoms. The data conundrum. The data we're going to use for this task is the publicly available PIMA Indians diabetes dataset. You can find, I will upload the link, but you can find them in popular machine learning repositories like UCI and Cargo. So in ML, it is very popular, just like the way the UN I think even the WTO has its own online dataset repository. So we have, there are also public dataset repositories like the UCI machine learning repository and Cargo. And here in this data set, there are lots of variables. So here you can see that this is not so simple. You know, in the previous example, because I wanted to show the case studies in increasing complexity. In the previous example, we had only one independent variable. Here we have lots of independent variables, over 10 independent variables. So the first independent variable is age. We have gender, we have polyuria, which means excessive urination. We have polydipsia, which means excessive thirst. We have weight. We have tiredness or fatigue. We have polyphagia, which means excessive hunger. We have genital truss. We have visual blurring. We have itching, irritability, healing, paresis, which means partial paralysis, muscle stiffness, hair loss, and overweight. All of these, all complex variables, some numerical, others categorical. Some having one or two categorical options, others having multiple categorical options. Since this is a non-linear problem and also a classification task, we can use any of the algorithms for classification. In this case, K nearest neighbors was used. So algorithms here for classification are in red and the ones usually for regression are in blue. So as you can see that most of them can be used for classification except linear regression. And the ones that have been asterisks can be used in both cases, both classification tasks and regression tasks. So now, I can't remember, someone asked that, how do we know which algorithm to use? So basically, it's not a guess. We don't guess. In applied machine learning, you cannot guess the algorithm to use. What you're going to use is an iterative procedure whereby you test all the algorithms and select which one best fits your metric. So for example, if it's a high accuracy you're after, you will choose the algorithm with the highest accuracy. However, in applied ML, we take into consideration computation time, but this is out of scope of the lecture. So yeah, what I'm trying to say is that you, first of all, when you have done your problem definition, your task classification, when it's now time to choose your algorithm, you must take cognizance of various things. Number one, what metric are you going to use? Are you concerned about accuracy? Are you concerned about, I don't want this I don't want this algorithm. Are you concerned about how well the algorithm does in a particular class? So what I mean is that, so for example, in this one on diabetes, we have the class of he or she has type 2 diabetes and they don't have type 2 diabetes. And you're saying, like, if you have an algorithm, for example, with an high accuracy of, let's say, 82%, but in the type 2 diabetes now, it is bad in recognizing people that have type 2 diabetes. That is not a very good algorithm, even if it has an high accuracy overall. So all this must be taken into consideration, your metrics. Now, a brief note on normalization. So who here can talk about what is happening in this, like in this particular data set frame, what can you notice that is different in each of these columns? What stands out to you? What do you notice that is different in each of these columns? Uye can answer that. Look at the columns. When I mean columns, like, from top to bottom, not left to right. So look at the columns. Each column, look at each column. There are 6 columns here. What can you notice about the numerical values in each of these columns? Antonia?
Yes, I'm not sure if this is what you're looking for, but they're not ordered.
Okay, no, that's not what I'm looking for. But yes, you're right, they're not ordered, but that's not what I'm looking for. So what you should be thinking about when you're looking at it is don't look at each particular column, look at column to column. So what I want you to look at is column 1, look at column 2, look at column 3, look at column 4, 5, and 6, and try to think like what is the difference between 1 and 2, 2 and 3, 3 and 4? Yes, Anna.
There's different digits, and column 2 is the only one that has variation in the number of digits. So there you have some with 3 digits and some with 2, and the others are more kind of similar.
Close. Yes, Catherine.
So you have single units, you have hundreds, you have decimals. It's all over the place in terms of the different numbers.
Yes. So Catherine and Anna are kind of right. They're heading towards the same direction. So basically, what is happening there? Let me go back. So basically, what we can see here is that in each column, for example, column 2, the digits are very high. You understand? We have 148 points, 85 points, 183 points, while in column 1 it's just 6 points, 1 point, 8 points. In column 5, for instance, 0.627, very small, 0.351, 0.672. There's going to be a problem if we use this data set like this. It's going to tilt towards, because the influence of column 2 will be too much compared to other columns. So how do we solve this? And this is what is called normalization. Yes, Antonia?
Yeah, sorry, I thought these columns refer to different variables, but I understand they're all about the same variable or the same observation. Is that the case?
No, you're right. They're all about different variables, yes.
So what you're saying is, like, if we use the numbers just in a multiplication function or a division function, then the impact of the smaller number would be lower than the impact
exactly.
Of the number.
Yes, Anna.
So we need to basically amplify the impact of the smaller ones to create something where we can gauge how much we take into account each of the variables.
Yes.
But we can
not really amplify. Not really amplify. We need to put them in the same level.
If we want
so that there's no influence.
to do that, right?
Yes.
But this goes back to Natasha's question. If we, for example, wanted to have something like where we influence the result because for ethical reasons, for example, we want to tilt the result of the AI output towards a certain direction, we could also use normalization to actually do that, right?
Yes, you could. Good observation. Yes, you could. Yes, you could. So what will happen in that scenario is that you're going to reduce the weights. You either reduce or increase the weights. And another thing you can do is to skip that particular column. If you want to leave the influence of that particular column, you skip it in the normalization process and you normalize the other columns. So now, I'm saying like the equation for a mean or average can be expressed as, this is, we all know the meaning of mean or average, summation x all over n, where summation x is the summation of the terms in x and n is the count of x. So an example is, we have ages of students in the classroom. We have 3, 4, 5 years old, 2 years old, 3 years old. Now to find the mean is what? Summation x, which is add all the ages of the students in the classroom, we get 17. Then the n is the count of x, that's the number of terms, we have 5. Therefore, the mean in this classroom is 3.4. Now, but here's the problem. What happens to the average age of the students in this classroom if a new child that's 2 years old joins, for instance? Who can answer that question? What will happen to this mean? We already have a mean, 3.4. Now, a new child now joins, that is 2. So we're going to have 3, 4, 5, 2, 3, and 2. What will now happen to this mean if a new child of that age joins?
It will decrease.
Yes, it may decrease or it may stay the same. Then what now happens to the average age of the students in this classroom if a new child that's 10 years old joins? Yes, Anna?
The average age will go up.
Exactly, the average age will go up. So what this particular slide is trying to talk about is the influence of outliers. And this now goes back to why normalization is very important. Outliers affect the overall average. So they affect the overall outcome, basically. So
Except
yeah,
if you tell the AI that if an outlier is too much out there, it should not take it into account, right?
you can do that in the pre-processing step.
Yeah.
Yes.
Yeah.
Yes. So in scenario 2, we can see that the average age of the classroom has increased because of the outlier 10 years old. It is always important to watch out for outliers in data, as can be seen from the example. And one way to combat outliers is by using normalization. This involves making sure the values in the different columns are in the same range. This in turn makes our model more robust and accurate in prediction. The metrics for measuring the performance of the KNN model will be accuracy score. For this task, it achieved an accuracy score of 0.8, which means that out of 10 samples, the model can predict 8 correctly. It is also important, interpreting the machine learning model's results is also important. So for example, if a model has an accuracy of 70%, what that means is that out of 10 samples, it can get 7 correctly. If it has 50%, out of 10 samples, it can get 5 correctly. If it has 90%, out of 10 samples, it gets 9 correctly. So you can see now that depending on the task, the metrics you're going to use and the model, algorithm you're going to use is also very important. Because yes, okay, you can say 8 out of 10, that's very good, you're happy, it's a good day and everything. But, in medical, for instance, in a situation of life out of death, what that means is that out of, for example, 10 people, 2 people may die. Out of 100, 20 people may die. So you see that it is very, very important and you must be really, really careful. Yes, Anna?
But even there, it links back to Natasha's question on ethics in a way, because if you know that most doctors misdiagnose more than 2 per 10, then you could say it's ethical to still use the AI, or you could say, no, we can only use AI if it's perfect, right? So you have a kind of ethical dilemma question there in the use of the AI.
Yes, there is an ethical dilemma there.
Well, it depends on the ethical framework that is established within the organization and the level of threshold that is acceptable. We'll discuss that in lesson 9. Thank you.
So what percentage is best? This depends on the nature of the problem and task at hand. For example, in the medical and health diagnosis, an accuracy of 0.8 may not be good enough, as that would translate to a potential misdiagnosis of 2 people out of 10, which can lead to severe conditions and repercussions. Hence, there's no percentage that's best, but a good convention is that if the model performs below 0.7, you should use/build another model. So which means that you should basically just trash the model or redefine the task at hand, the machine learning task at hand, going from the problem definition to the task classification to the data. It must be redefined because any model below 0.7 is not good enough. So class activity, So this is for everybody. You can do it as a group. I want you to craft an applied machine learning task for the WTO. So yeah, what I want you to do is the 5 tasks. But for this purpose, let's just do 4. So I want you to define a problem. I want you to decide what kind of task classification is this problem. I want you to decide, okay, what kind of data am I going to use? How will the data be? Then I want you to choose a machine learning algorithm. So 5 minutes.
Yes, an important task within the supply chain environment, from production to distribution. Just look across the entire supply chain.
Yes, Anna. Oh, okay.
So we're each gonna do this individually, or how do you want us to go about this?
You can do it individually, but once I hear 1 or 2 or 3 ideas, then I'll move to the next slide.
So, and you want something from supply chains?
No, it could be anything, but yes, Dr. Ike said supply chain, but anything that you feel there's a particular problem at the WTO in the office and stuff, and you want to use ML to solve, you want to use AI to solve, it's just abstract, just, define the problem, think of the task classification, the data that you're going to use, and choose an algorithm for it. That's all. It's just a class activity, that's all, yeah.
I mean, I think so. For example, if you think of our world, like the trade reports that we're doing, right now we're looking a lot into what would happen, for example, if 2 countries stop trading with each other, and what happens to overall economic output and other, like, to trade patterns.
That's good. That's a good. So in that problem now, what is going to be the tax classification? Are you going to, what tax classification is that going to be?
You mean whether it's regression or?
Yes, or classification. Is it going to be a regression tax or a classification tax?
I think it's a regression task.
Regression tax, okay. So which algorithm would you be using for it?
First of all, let's establish why it is a regression task. Anna, why do you think it's a regression task?
Well, because you're looking at numerical values on a spectrum, not like a black and white kind of thing. And yeah.
So for Anna's problem, the problem definition is that problem definition is 2 countries. You're trying to decide, you're trying to create a scenario whereby if these 2 countries stop trading with each other, what's going to happen. So already there's already data of the trade volumes between the 2 countries. You understand? So we're going to have that. That's going to be 1 column. After that, we're going to have the years they've been trading for. You understand? We'll have the years they've been trading for. I have a column. we can choose something from Natasha. So we can say, let's have let's have something like maybe the governments that were in power. You understand? Was it Democrat? Was it Republic? Was it Green Party? Whatever government that was in power, that can be another column. You understand what I'm saying? So based on that, we can now begin to define what our target variable is. So the target variable can be impact of not trading, for instance. What's going to happen to the impact of not trading? So that's going to be our target variable. And are we going to look at that? That is where, the domain, things like domain knowledge will come into place, and rigorous thinking is going to come into place there too. So, but the key giveaway here is that in applied machine learning, there is no one way to solve a problem. I need everybody here to understand that there's no one way to solve a problem. There are different ways that you can use to solve a problem. That's why it's called applied. You understand? That different ways. It could even be something else. We could be looking at, let's say for example, there was this paper that I wrote with Dr. Celestine whereby we looked at sentiment analysis of COMESA, for instance. So we could even create like sentiment analysis of maybe the trade policies between these two countries over the years. Is it steadily increasing, like how positive it is? And we'll use VEDA to get the sentiment score. So how positive has it been over the years? Is it increasing in the direct, is it increasing? Is the sentiment increasing? That's positive. Or is it reducing? That is negative. You understand? So it may not even be, we may not even frame the problem definition as a structured variable, like with columns and rows. It may be something else. We may use natural language processing, for instance. You understand? We may look at, okay, we want to analyze the social media. You understand? Social media sentiments, like in those two countries over the years. So that can also be another defining variable that, okay, based on this, in this particular year, if this happens, if it's negative, So it depends. My point is, in applied machine learning, there are various roads to use to solve the problem. There's no one road to solve it. Hi, Tran. You raised up your hand before, Tran.
Yes. Like one example, one case I can think of, like we support a group of like 45 very poor countries, and we want to kind of the target to increase their trade in the global, their share in the global trade from 1% to 2%. So the question is, how much technical assistance or aid for trade and investment need to go to those countries so that we can design our program accordingly. For example, this case. And we have the data on, a current aid for trade flows into those countries, the current of foreign direct investment. But if we want to reach the target of double their trade share their share in the global trade, could the AI can help in that mode?
Yes, yes, it can. It can help. Yes, definitely.
Yes,
it can.
I think there are various areas where AI can assist, but the underlying this is data. First of all, we want to understand the comparative advantages of these countries in relation to the global environment. We want to understand their trade policy positioning. We want to understand the laws and regulations that are at play there within these countries, and how they are able to use those laws, the rule of law index, the democratic corruption index, and all of that. We need to understand the entire macro the situation or positioning of these countries. Once that is established, then the trade flows that currently happen, the structural issues in those countries should be looked at as well, and how it inhibits trade. If it's a region, you want to understand the regional connectivity, currency convertibility, you look at infrastructural connections, you look at a lot of variables that would sit within this context. But at the heart of it is the idea of their comparative advantage. Thank you.
Yes. Dr. Ike is right. But another thing that you notice is that what a lot of times what causes the discrepancy between in trade volumes in the rich countries and the poor countries, a lot of times is because a lot of the poor countries focus on raw materials. So that usually they export raw materials and then they now import finished goods. So already, because finished goods are usually worth more than raw material, so already there's already an imbalance. So the only way for them to actually increase the trade share or trading volume share is for them to be more industrialized, basically. That is just, but yes, we can use ML to be able to give definite numbers and impacts and forecasts and for anything predictive modeling, basically, which will be taught in the next lecture. Okay, so that's it for class activity. Now, case study 3, more customers data. Remember the 5 steps, but for this lecture, 4 steps: problem definition, task classification, data, and the machine learning algorithm. The problem definition: a retail outlet in a commercial mall wants to better understand the spending patterns of its customers in order to be able to better perform customer retention and targeting strategies. This is a tax classification. In this tax, we want to be able to segment the different customers according to their annual income and spending patterns. We want to use an unsupervised approach, clustering. I'm sure that in the previous lecture, Dr. Pradeep spoke about the 2 branches of ML. We have these of ML algorithms. We have the supervised learning and the unsupervised learning. So basically, supervised learning is everything we've been doing up to now. So it is you telling, okay, the algorithm do this, do that, doing the pre-processing and everything. The unsupervised learning is the opposite of it. The algorithm is the one making all the decisions all the time. You understand? Most of the time, it makes all the decisions. So one area where unsupervised learning is usually applied is in clustering. And this is an example of a clustering problem, and we're using unsupervised learning to solve it. So yeah, we're using the k-means clustering for the classifier. The k-means will be spoken about more in the next lecture. But in order to use the k-means, we need to find the efficient number of clusters. So basically, what is happening is that before we can apply the algorithm, we need to know, okay, what is going to be the efficient amount of k, which is clusters, in this particular data. So right now, what is happening is that, let me open I want to open the data set. So can you see the data set? Can everybody see it? Yes. Okay. So here we have 5 columns: customer ID. We have the gender, not gender. We have the age. We have the annual income in thousands of dollars, and we have the spending score from 1 to 100. 100 being high, 1 being low. And here we have close to I think 201 customers in total. So we have this data now, but what is happening is that we want to be able to know that, okay.
A hand is up.
Sorry,
okay, yes.
One quick question.
Yes.
The fact that we're using clustering means we have a classification task at hand?
Yes.
Is that correct?
Yes, it's a classification task, yes. So what is happening here is that this is a retail outlet. They want to be able to, like, for example, they want to be able to send email newsletters now on new promotional offers. But they don't want to send email newsletters to people that would not read it. You understand? They will not even open the email. It's a waste of targeted marketing. They want to be able to target the right people. So that's where clustering comes into place. It creates like clusters of people that, based on the given data, they will be grouped together in different clusters. So here we have seen the different variables there for this clustering problem. So now, yes, before I forget, so we have two screenshots below which contain the data for the more customers. We have the customer ID, gender, age, annual income, spending score. This is fine. Yeah, this is a structured data because it's neatly ordered in rows and columns. But one field assumption, I'm sure, because some of you must have said, oh, this is very easy. I can use my eye and my experience, is that we can use an eye test to say, okay, yes, based on this, okay, this is the right way, this one and this one and this one. Okay, let's test it. So now let's look at the first one. We have, let's just focus on age, annual income, and spending score, for instance. See here now, in the first one, we have, we have here the first row, customer ID 1, the gender is male, the age is 19, the annual income is $15,000. The spending score is 39. Okay, let's assume anybody that is young and is earning below 15,000 does not have a high spending score, right? It's a fair assumption. The less you earn, the less you'll be willing to spend. But look at the second one. Just the second one, our assumption has been broken. The second customer, gender, same gender, male. The age is 21. The annual income is $15,000. Same annual income. But look at the spending score, 81. What does this mean? This is a low income earner with a high spending score. So this individual spends a lot of money despite earning low. So yeah, now this is where Dr. Ike will now talk about things like the ethical issues now, ethics now. Should we, as a retail outlet, should we still market to this person or should we ignore? So now we can see the importance of clustering now. Now let's look at another one. Let's look at female now. Let's say, oh, okay, these ones are earning low. No. Anybody that is earning above 100,000 would spend high. No problem. Yeah, now we can look at row number 187. This is a female. She's 54. High income earner, a manager or something at work, earning $101,000 a year. But look at her spending score, 24. Oh, we can say, oh, okay, she's 54, maybe she's a grandma, she has children, blah, blah, blah. Let's give another excuse. All right, no problem. Let's look for another one. Look at this male. Okay, he's a different gender, fair enough. He's 33. That is row number 193. He's 33. He's earning $113,000. He's even earning more than female. And look at the spending score, 91. So you can see that we cannot use eye test to understand this data. We cannot use eye test to guess this data. We need to use an algorithm. So now, using the first 8 rows, another class activity, we'll do this. This time we'll do this together. Okay, let's do a bit time. 5 minutes. Let's turn this clustering problem into a classification problem. Now, we have a cluster. Sorry, I gave the answer. Okay, so we have a clustering problem. So the activity is to turn this into a classification problem using the spending score column as your dependent variable. So what is it that I'm trying to say or trying to do? I'm saying that now we have these 5, sorry. Just a minute, please. So we have these 5 columns: customer ID, gender, age, annual income, spending score. When I'm saying based on this spending score, let's create another column here so that we can turn this into a classification task. So how can we achieve this? Based on spending score alone. So this aspect, I'm introducing everybody to data engineering, which is the next topic we'll be discussing. So based on this spending score, that is this column, I want you to create another column. Just suggest another column, anything, create another column, and let's have different values for the different rows in that column. Yes, Catherine?
So for this column, I would suggest saying type of spender, and then you could make categories that are like low spender from whatever 0 to 10, medium spender,
Yes.
and then high spender, 100 plus.
Yes. Catherine stole that from my head. Yes, she's right. That is, yes. So we'll have like, what we're going to have is, the type of spender. So once we have that, then we can now decide that, okay, this is now a classification task, and we'll no longer be using the clustering algorithm anymore. We'll use a classification algorithm. So you can see that still comes back to your question, Anna, that you could have in that class activity, you could have a particular problem where you give that problem that you described at with the WTO regarding those reports. So there are different ways, and I said that there are different roles you can use to solve that problem. You understand? So this was a clustering problem, and now we've turned it to a classification task, and we can still turn it to a regression task if we want to. So here is now talking about the final output of the clustering algorithm. We can see that we'll be using the k-means clustering algorithm. There are other clustering algorithms you can use. I think there's another one called the hierarchical clustering algorithm, passing the following arguments to the parameters. 3 parameters. In the data engineering, you come across parameters, and I'll explain that in a bit more detail. We have the n underscore clusters, which is 5. We got the 5 from the number of clusters when in the previous slide when I was talking about using the k-means. So this was why this was the reason why we did this process, to be able to pass that particular value into that parameter as an argument. I'll still discuss parameters arguments in the next slide. The init function, which is the k-means plus plus, and the random underscore states is a parameter used to make sure that you always have the same outputs based on a given input. And here, which is the most important thing, this is the application of everything. So here we have 5 clusters. So we have the is this turquoise? We have the turquoise cluster here, the top left. We have the hot pink cluster here. We have the red in the middle. We have the green. We have the blue. And look at all the clusters here. This the labels, showing us the labels. And now on the x-axis, we have annual income in thousands of dollars. On the y-axis, we have the spending score from 1 to 100. And here now, for example, let's say, look at this green cluster now. We have people with an annual income of 20, spending there. We can say this green cluster is people with low income and maybe low spending habits. We can make that assumption. It's fair enough. However, in the turquoise here is a cluster of people with low income and high spending habits. Like in the example of the male that was earning 15,000 and had a spending habit of 91. In the red here, we have people of middle income, depending on the country. Middle income, that's like between 40 to, okay, not really middle, above middle income, with also middle spending habits. They don't spend so much that, okay, this, they earn, they're in the middle, they're in the middle in both ways. Now, here we have the blue cluster, those with high income and low spending habits. The retail, they will not be interested in these people. They're, should we say, stingy, or they're miserly. It could be anything, it could be any reasons, but maybe they just don't want to spend in that particular retail outlet. But here now, the hot pink, this is where they will be putting their target, their marketing to, because these people have high income and they have a high spending habit. So this is where they'll be putting the marketing efforts into. And in some scenarios, as Dr. Ike will mention, in a way, it is even by law in some countries. Like, for example, in the UK, I know that if you have a particular income threshold, you cannot participate in gambling, for instance. So so the ethical reasons now come into play in that kind of scenario, So now this hot pink cluster is high income, high spending habits. Now, I want to talk about data engineering. Data engineering can be loosely defined as the process of transforming data from one form to another. Various reasons can account for this, from getting more insights in the data to expected inputs into the classifier models. Now, I'm giving an example. We have a variable called gender. And in this variable called gender, we have 5 people. We have male, female, binary, female, male. Here we have 3 different categories. Computers only understand numbers. In fact, all code is eventually converted to binary numbers, zeros and ones. In this case, let's use one-hot encoding, a common encoding algorithm for categorical variables. So we're encoding the male gender. Anybody in the data set that is a male, we're encoding them with 011 and the same thing we're doing for female and the same thing we're doing for binary. You can see they all have different encodings. So after transformations, the gender becomes that based on the one encoding we've done. In some applied ML tasks, data engineering is a core and important step because the data would need to be engineered before we can build machine learning models. All machine learning models are expecting a numerical input of some kind. And yes, this even includes those pictures that you saw whereby we were trying to identify if one feels drowsy or not, or even text. So like anything like all those like trade policy documents, for instance, if you're going to want to analyze or know the sentiment, for instance, you will have to turn those texts into tokens, and those tokens will be turned into numbers. So data engineering is important in machine learning. You cannot escape that. And look at a practical example of, okay, we have a question from Anna. Yes.
Yeah. Simple question, like who does that data engineering? So in a simple, like if you have these more traditional forms of programming a computer, it would be a human basically engineering the data and telling the computer how to do this, right? Yes. But in AI, it would be the AI doing this for me. Or how does it, like,
yes,
who does
the AI can do it for you, but to be honest, you need to understand, even if the AI is doing it for you, you need to understand what the AI is doing.
Yes, exactly, because this is of course something where you can get a lot of ethical questions and bias into your model.
Of course, yes.
And
yes.
so you want to know what that, so that's why I'm asking, like, is it the AI? And how do I then control what the AI is doing? So I need to be aware that I'm giving the AI the power to do this for me. And I need to be able to basically question the AI on what it's doing and understand what it's doing if I want to see whether my model can be trusted or not, right?
Yes, you're right. You're right about that. The honest truth is that data engineering is actually a field on its own. There are actually people they are data engineers. That's their work. This is what they do. However, modern AI has the capabilities of doing this tasks for you, but it's also important to understand what it is doing. So, for example, now a good example is for a dependent variable. Let's say we have a dependent variable like in an health classification task, for instance, if one has malaria or not. And let's say we have just 2 outcomes in that variable. You either have malaria or you don't have malaria. In that particular scenario, you can't use one-hot encoding, for instance. You understand? So one-hot encoding cannot be used. It's not advisable to use one-hot encoding in categorical columns that have just 1 or 2 variables. That one you use ordinal encoding for that. You understand? So to know each tool to use it for each scenario, because all scenarios are different, you understand? But at the initial step, you understand, if you want to get something quick and going, yes, AI can help you. It can help you with that, yes. And here we have another example of data engineering. Here, what we're doing here is basically signal analysis. So this is in audio engineering, in the domain of audio engineering. So the left-hand side, we have the waveform of an audio file, and the right-hand side, we have the spectrogram. And you can see that, when the algorithm listens to the audio, picks the audio or saves the audio, we now have to extract features from it. So this aspect now is now called feature engineering. I don't know, I think Dr. Pradeep must have mentioned it in the last lecture. Okay, fair. If he didn't mention it, maybe Anchal may mention it, but let me see. Okay, I'll briefly talk about feature engineering. So basically, feature engineering, as the name suggests, is used to extract features from data. It is usually used in mostly unstructured data. So when you have things like, pictures, like media data, pictures, text, images, you have to use feature engineering. You understand? So what it involves is similar to data engineering. The only essence is that in feature engineering, there are lots of transformations taking place. In audio, for instance, which is a different field, audio engineering, I'm using the MFCC algorithm, so male frequency algorithm, basically. But all that is not really important. The most important thing is that we have an audio file, and the waveform is showing the pitch of the audio file, and the spectrogram is also showing the hertz of the audio file. You understand? And this audio file is now transformed into this array of different numbers, and this is just one audio file. All this is just one. In fact, the person said, I think this is for SEEK, exactly, SEEK.M4A, just SEEK, and this is what it has transformed it into, just one file. So you can see that it is actually very important. Data engineering and feature engineering is very important, because imagine if we're trying to do an analysis on, let's say, a 1-hour audio file. Imagine the deluge of data one is going to have, if this is just one word. Data engineering is extremely crucial in the domains that deal with unstructured data, images, text, audio, etc. It is also used in structured data, especially in pre-processing and gaining further insights from the data. Now, we want to engineer data for a microeconomics problem, profits. This should be similar, familiar with everybody here. So in economics, profit is defined as revenue minus costs, and revenue is defined as price times quantity. And in cost, we have two types of costs: fixed cost and variable costs. So for this practical session, let's imagine a fashion house that manufactures the following items: shirts, trousers, watches, belts, and heels. And from these following items, we now create a data set. We have the product ID, the item, the raw material, the overheads, marketing, labor, sales, and quantity. So now, what is the problem? What are we going to do now? We want to engineer the data. From this from all these variables here, from all these column names, product ID, raw material, overheads, etc. We want to get what is our total costs, what is our revenue, and what is our profits. So how do we go about that? The way we go about that is very simple. We just create another column here. This is using Excel, but this can be done with Python. But because Python will be introduced in the later lecture, and I will also talk about it here later on. So what we just do is that we have a column called costs. We have another one called revenue. Then we now have the last one called profits. So yeah, what we're doing is we're trying to engineer this data because we didn't have these 3 variables before. So we're trying to engineer this data now. So now our cost is, we said from the formula, we said it's fixed cost plus variable cost. Fixed cost is, things like land, mostly immovable cost and stuff. And it's also, I think it depends on industry, from industry to industry. Some industries, some things are fixed costs, in other industries is not. Variable costs are things like overheads, labor, those are variable costs, for example. Cost of raw materials are also variable cost, for instance. And here now we have, raw materials, overheads, marketing, labor, sales are quantity. Those are not costs, so we don't care about that. So already, I think I've already given the answer, to be honest. So the the total cost is from column C to column F. Will give us the cost here. And that's how we fill the different costs in these variables. Then the revenue. What is revenue? That's very simple. That's price times quantity. So how do we do that? So we take the sales price here and we take the quantity, we multiply both of them, and we have revenue. Then for profits, this is very simple. We've already engineered the one for cost and we've engineered the one for revenue. So what do we do? Where's the formula? For profit is revenue minus costs. So all we just need to do there is minus revenue from cost and we get profits. And we can go on and on. This is how you can begin to create your data set. You can begin to create your task and everything. You can keep going, depending on your domain. So in supply chain, it could be anything. It could be maybe routes. It could be import tariffs, anything. You just keep, and from there you can now begin to get to engineer the data. Which other column do you think we can get from just this items here? 1, 2, 3, 4, 5, 6, 7. What else do you think we can get? There's a question. What else do you think we can get? Which other column do you think we can engineer from the current columns we have now?
Yeah, I think, may I?
Yes, Tran.
Yeah. I think we can be used to analyze as well, like the sectors where the kind of the linkage between profit and job creations, like what are the products that create more job and have a more profit, or more job but less profit, this kind of thing. And if a link to overhead, like if I have to reduce the overhead, then what kind of the product I need to look at? Is it possible? Yeah.
Yes, it's possible. That's a fine suggestion, Tran. Yes, it's possible. So so in that scenario now, we want to know that, okay, like, some of these items now, because labor is fixed, is $11 per hour, and we're looking at these items that, okay, this one. So how to do it is that we want to know, okay, 11 divided by 55 is 5. So it takes labor 5 hours to make this quantity of shirts. You understand? To make this quantity of shirts, rather. You understand what is used in labor. But of course, we know that is not possible because there should also be a column for machinery. But just for the purpose of this lecture, let's just say something like that. So we can look at, okay, lists most profitable item. You can have this thing for most profitable item. So that is the item that is the cheapest to produce, basically, will be the most profitable item. Do you understand? And one way to get that is we don't even need to because by the time we've gotten, okay, let's say we have this column, we'll call it profitability. So by the time we get this column, we can already know what is going to be the most profitable item. You understand? By the time we have this profit column, because we're going to get profit per, but that is also because each of these are selling a different, or we can say maybe most popular item, for instance. That difference, it can go anyway. It can go anyway. But basically, the main takeaway is that when you have a particular set of data, we can engineer the data. And in the next slide, I'll bring that point home. So now this is one that is much more familiar to everybody here. We're looking at trade balance. And we're saying that trade balance can be loosely defined as total exports minus total imports. So we all know that if trade balance is positive, that's a trade surplus, which is what most countries want to be in. And if it's negative, that's a trade deficit. And here now we have, for one country, Australia, we have these trade volumes from 2003 to 2023. Let's look at the data. But okay, yes, so we have the years, the country is Australia, we have the inflation in percentage, the annual inflation, we have the export of goods and services in dollars, we have the imports also, then we have the GDP per capita. But what we're interested in is in trade balance. And over here, we do not have any column for trade balance, but we can engineer this data set in order to get the column for trade balance. So the class activity, which I'll be taking it this time, data engineering for Australia's trade balance. The tool I'll be using will be Google Colab. So basically, Google Colab is an online IDE, integrated development environment. Basically, is what usually programmers use. But even for this task, you can use Microsoft Excel. But I just to add a little bit of variety, let me also use Google Colab here. Think of this as like Microsoft Word, but for programmers, basically. That is what we can think of this as. Let me see, what's it? Okay. That's what we can think of this as. So the first thing first is, we want to get the data set. And I think the first thing is for us to look at the data set first. We've seen it before, but this is what we have. We have the year, we have the country, inflation, exports, imports, and GDP. So what we're looking for is we want to get the trade balance. So the first thing I have to do is to import the file. So now I've imported the file, and we can click on it. So in order to use the same, no. Okay, because it's an Excel file. So in order to use the same tool with me, all you need to do is go to collab.research.google.com, log in with your Gmail account when you get home. So the first thing we need to do is, the programming language I'll be using is Python. Python is the programming language for machine learning and AI, basically. That is what we use in machine learning and AI. Some people use R also, or maybe other languages like Julia, but Python is the convention in machine learning and AI. And what I need to do here is I need to import some libraries. What are libraries? Libraries are things that extend the, like small programs that extend the functionality of a particular programming language. That is what a library is, that's what they do. So I need to import 3 libraries. The first one I'll be importing will be a library called numerical Python, or NumPy. Some of these things in the next lecture, Dr. Ancha will explain in further detail. So here is just to show you how to achieve this, that's to engineer the data in a different way. But this can be done in Excel. So I need to import pandas also. Then I need to import for visualizations, visualization purposes, matplotlib. So we've imported it. Now the next thing is, now that we've imported those libraries, we need to be able to read the Excel file. This notebook will be uploaded on Moodle, so you can later have a look at it and practice at home. So what I'm doing here is that weight balance. So what this line is saying is that we want to save this data, this Australia data sample. That is, we want to save this. That's this file. We want to save it into a variable. The name of the variable is data, and what then we're not saying how are we going to be able to read this data. That's why I imported this library called pandas. So we're telling this library we're calling a function or a method in this library called, excuse me, read_Excel, and this would what this method would do is that is the same thing as what Excel is doing. Basically, it will give access to Python to this particular file. Then we can begin to manipulate it and all. So yes, so that is done. And now we want to see, let's see the data. Let's see the first 5 rows of the data, basically. And so yeah, we can now see the data. So you can see that roughly is like the same with Excel. There's no difference. So now we can now see the data here. And if you want to see the last 5 rows, we call the method called tail. That's all. And it will show us the last 5 rows. However, so it's good that I've said this. So yeah, now there's a problem. The problem here is that for some reason, because of I don't know, this file Excel, so it is getting it up to, I don't know, it stopped at, it truncated it at 101 or 102. I know, but that is not a problem. Another thing that we need to do is we want to know some particular information about this data. So all we need to do is data.info, so we want to know the variables involved in the data. So yeah, we can see that we have 7 variables. There's some variables we'll have to delete. So we have country, year, inflation, imports, exports, and GDP per capita. So after that, what we need is we need to truncate this data because, like I said, you can see that every other variable here from 1 to 6, the count is 21, but this first variable is 105. You understand, because of what I explained earlier about Excel. So we need to truncate data. So what we do to truncate is there are different methods for this. So you can use the index locator or just the locator. But I'm going to use the index locator for pandas. And yeah, what is happening is a sort of slice. Hopefully in the next lecture, Dr. Ancha will explain much more what is happening. But basically what I'm doing is that, let me just use Excel to explain what I'm doing. So basically what I'm doing is equivalent to doing this. No, sorry. Answer. What I'm doing is equivalent to doing this. That's what I'm doing. It's the same thing I'm doing with code. You understand? Because I don't want all these other rows to be there. So it's like I'm trying to just copy only this particular segment. So that's what I'm doing that code, and that's it. So I want the first 21 rows, and when we now get that, we now want to make sure that it's the first 21 rows, and now we can now get the first 21 rows. So now the next thing we want to do is we want to drop these two columns, which is country and CTR.1. So all these are part of like data engineering. So we want to drop these two columns because we don't need, it's just one country in the data. It's only Australia. You can see here that it's just Australia that is here. So it's a tautology, to be honest. So I want to drop that column. So to do that is we'll do a brief some manipulations. Basically, we have to select we have to tell Python the columns to drop, basically. And the first one we want to drop is this CTR. We want to drop this country. The next one we want to drop is this other column that is also similar to CTR, but is called CTR1. So CTR.1. Remember, it must be the way it is here. So when we drop that, then we now want to say what happens is that for this method, when you use this method, it creates a copy of the data frame. So what is a data frame? A data frame is a type of data structure, basically. So in computer science, we have different data structures. We have lists. I mentioned list here. So this is like a form of like a list. So we have lists, we have dictionaries. They're different, but that's not important. You understand? But what I'm saying is, for this data frame, whenever we want to drop a particular column, it creates a copy. But we're not saying that, okay, no, don't create this copy. We want it to use that, put the result in still in the same column. Then the next parameter is the axis. What does axis mean? Shit. So axis means that remember then in the lecture when I was saying x-axis, y-axis. So basically that's what it means. So anything vertical is the y-axis and horizontal is the x-axis. So basically just like in the Cartesian plane. So that's what will happen here. So basically when we do that, so we've dropped those columns. So now let's just find out. So now we now have year, inflation, exports, imports, and GDP. So now it's been engineered and it's perfect now. So we can now continue what we want to do. So now let's just view let's view, for example, let's view year. So so this is our year, and we can use that to view the other columns. But for now, you can see that for some reason, when we imported this year, you can see another data engineering problem. So when we imported this year, it turned each year into floats, and this doesn't make sense. There's nothing like 2003.5. It doesn't make sense. It's just 2003, 2004, 2005. So in computer science, we have also what we call data types. So these are called data types. So things like age, numbers, that are called integers. Then things that have decimal values like inflation and stuff are called floats, for instance. So anyways, what I need to do is I need to convert this column from floats to integers. So what I need to, how I do that, one way to do that is not the only way. One way to do that is to select the year, then call a method on it, then turn it to an int. And when we now call the year again, so you can see it has been transformed. So you can see, for example, a real life example of engineering the data. So we transformed it from a float to an integer to, yes. So the next thing is, so let's do the main thing. Let's, so let's do the main thing. Let's, so let's do the main thing. 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 So let let's engineer the data to be able to get the trade balance, because that's what this is all about. We want to get the trade balance. So what we need to do here is using this method. You can also do this with Excel. So when we get the trade balance, we have to call the trade balance. You can see that I'm still using the same way, but now what we want to do is for this data frame, we want to add another column at the end. So that's why we're calling the column. You can name this column anything, is left to you. So when we name that column, what we need to do is we need to call two columns. Exports, total exports, trade balance is total exports less total imports. And we have it here. And this will give us our trade balance, basically. And then when we call, let's get the first 5, then we now have it here. So you can see we have the trade balance there now, the new column there. When we have the new column there, then we can, let's get more, because here now you can see everything is, so which means Australia from 2003 to 2007, Australia had trade deficits consecutively. And you'll see something very surprising. In the last 5 years, Australia has had all trade surplus. So what could be the reason? I think that I'll leave that as an assignment for everybody to find how come Australia now has a trade surplus in the last 5 years, but from 03 to 07 they were all trade deficits. So something is happening over there, or a policy kind of changed, or there was a shift. So the last exercise is just to see, let's just see the basically, let's see the trend in the trade surplus of Australia over the last, from 2003 to 2023. So in the last 10 years, or what has been the trend in the trade surplus in Australia. And yeah, what is happening is you remember that at the beginning I called the matplotlib. So this library, so it's a plotting library, basically a visualization library. You can go to let me see. They have a documentation. The good thing with all this is that if all these libraries I'm using have a documentation, so this is visualization with matplotlib, and you can read about it and use it if you want to. But I think Anchal is going to teach everyone a more tools with GUIs, that's graphical user interface tools that you can use. That'll be much easier, maybe much easier. So yeah, now what I'm saying is I want to get just this column, trade balance. When I get that column, I want the color to be red. That's the line of the color to be red, the trend of the line. Then I'm now putting a label to the y-axis, trade balance. Then this is just to the title of the column. And this is just to make it for it to show. That's this particular chart for it to show. And there now we can see the trade balance in Australia. As you can see in this chart, this is 0. So anything up there is positive and anything below is negative. And you can see that at the beginning it was down, everything was almost negative. Then it began to spike up. It was inconsistent here. Then from here, this particular year, maybe I think this is like 2012. Let's see. Let's check it. Data. Mm, mm, uh, so okay, from like 14. So 14 will be from 2018. No, 2017. So this would be like from 2017, and the trend increases over time. So that is one example of engineering data in order to get more insights and prepare it for a machine learning model. So we also have something called media data. Well, I've looked at it before. I've looked at media data before. We looked at audio. This is a waveform. This is a spectrogram. But we have not looked at, for example, CT scans, computed tomography images, basically. So this is an example of a CT scan. And all these are samples of media data that would need feature engineering and data engineering in order to be able to feed into the machine learning model. So all these are applied machine learning tasks. So discussion and questions. Any questions so far? Or any question at all, basically? Yes, Emanuela.
Thanks. You mentioned a number of machine learning algorithms at the beginning, and you said, well, the best way is to test them and then see the one that gives the best results. But is there a way to have an idea of which one is better in which type of situations? Are there pros and cons for each model, or is it really random and they have to be tested and whichever gives the best results is picked? But is there a way to have a sense of which one to use?
Okay, that's a fine question. Because a lot of these algorithms, there are underlying principles to them. So, for example, like I said at one point, let me see. Okay, is in a previous slide. I said some of these algorithms are probabilistic, which means they're based on probability. So one famous example is naive Bayes. So it's based on probability. So, you know, some are based on trees, like decision trees. Some are based on like support vectors, like the SVM, support vector machines. Some are based on neural networks. So to answer the question, it will determine on the task at hand. So for example, now let's say you're trying to maybe the problem is the problem that you have, you want it to be based on probability, that okay, if this happens or it doesn't happen, then you use a probabilistic model, which is like something like naive Bayes, for instance. You understand? But if you want something deterministic, that oh, this is going to happen or this is not going to happen, you understand, you can use something like the trees algorithm, for instance. And also you can also combine both a probabilistic model and a deterministic model in order to get the both of two worlds, in order to create an ensemble. Excuse me. So another thing is you also look at the issue of the metrics. What are the metrics I'm going to use, at the end of the day, when you have done your task classification? What are the metrics I'm going to use? What am I actually looking for? Like if it's health now, accuracy is very important to you. You understand? So, but if it's something like if it's something like a regression task, for instance, maybe the government is trying to, cut down inflation. You understand? In that one, the mean squared error is very important to you. So, so it all depends on the task. There's no particular rule. They're just conventions that, okay, if you want to do something based on probability, use probabilistic models. If you want to do something that is deterministic, use deterministic models. And if you want the best of both worlds, you can use an ensemble. But neural networks, for instance, is usually very, very good for unstructured data. So yes, that one is more than a convention. That one is like a rule. Neural networks are, in fact, yes, they're usually good for, yes, they're used for the generative AI that is very common now is based on that, the underlying foundations of it. So neural networks are good for unstructured data.
Yeah, just a quick follow-up before you take the questions from the participants.
Yes.
As a follow-up to Tran's question, when she spoke to different countries wanting to trade together and the idea around how to work around the best model to help assess whether these countries can work together. What sort of models are you looking at there? Could it be predictive model? Are you looking at a model that will predict future trade flows between these countries based on the underlying variables, or you're looking at a different category here? Thank you.
Dr. Ike, is a question for me or for Tran?
Yeah, it's for you.
Okay, it's for me.
Larry.
Okay, it's for me.
Yes, I just wanted you to, just as a follow-up to Emanuela's question, to suggest to her the sort of tools or the algorithm that is appropriate.
Yes. I think in Tran's case, first of all, like the problem has to be clearly defined first. Also, there's also the issue of data, because I remember you mentioning some things that they can add to the data. So we have to look at, okay, that data, is it available? Because you can only build a model on available data. We have to be realistic, so you can only build a model on available data. So is the data that is available that will not determine the kind of task we're going to do. So whether it's going to be regression or whether it's going to be classification, you understand? But at the end of the day, like I've said earlier, any regression task can be turned to a classification, and a classification task can be turned to a regression.
Yes, a question from the others. Yes.
Yeah. Okay. Anna. I think it was Anna first before
Jonas.
Yeah.
Thank you very much. I think you started talking a little bit about this, but how does your lecture today relate to the concepts of supervised versus unsupervised learning that we had in the previous lecture?
Everything. Everything, it relates everything. In fact, like if you didn't go to the previous lecture, not to the previous, I mean, if you didn't go to the first lecture, which is fundamentals of AI, this lecture one would not even understand this lecture basically. So in the fundamentals of AI, Dr. Pradeep introduced supervised and unsupervised learning and all. While in this lecture, what I'm doing is which scenarios should you use supervised and which scenarios should you use unsupervised? You understand? But there was just a focus on supervised learning. But the unsupervised will be an example will be clustering, for instance, the more customers data we did. So that's an example of unsupervised learning, for instance. So it is Dr. Pragdison was an introduction of the fundamentals of AI, and here's the applications of AI that you can use in your own work.
So if I look at these, sorry, I'm still not 100% clear about this. So if I look at these different types of algorithm that you're giving us there, would some of them fall into the category of supervised and some into the category of unsupervised learning, or how do I determine like?
So for the very fact, I'm sorry I didn't even mention this earlier. So for the very fact that we're even choosing an algorithm, this has already made it supervised.
This has made it supervised.
Yes,
exactly.
this has made it supervised.
So most of our lecture, what we were talking about, the data engineering and all of that, that would mean that we're in the area of supervised learning.
Yes, supervised learning, yes.
Okay, yeah, that's what I wanted to make sure.
Yes.
Because I wasn't sure whether how this applies, for example, to unsupervised learning. But in unsupervised learning, you wouldn't be doing that.
The thing was I didn't really touch on unsupervised because it's a bit more complex. So I didn't really touch on unsupervised learning, but I still touched on it in the more customers data and the clustering example that I gave, so that is an example of unsupervised. And for unsupervised, I said like there are two major algorithms, which is the k-means clustering and the hierarchical clustering. But the k-means is the one that is usually used, is a popular clustering algorithm, and that is in what slide was that? Let me see. I think that was
on your slide there. That's the k nearest neighbor.
No, it's the k-means was. So this is the clusters, but I mentioned no. What kind of tax is this? No.
Yeah, we had it. Okay, so
I
if
think
if I use any of these algorithms,
yeah, exactly.
I'm in supervised learning. And I will use something different for unsupervised learning if you boil it down to something very simple. Is that okay?
No. That's not it. That's not it. What I'm saying, sorry, no. What I'm saying is that in machine learning, we have like two major algorithms. We have supervised learning and we have unsupervised learning. So supervised learning is when you now are the one telling the algorithm what to do. You're the one in charge of the inputs and all those things. You're supervising it.
Yes,
You understand?
exactly.
But in unsupervised learning, you're not supervising it. So the machine learning is the one coming out with the insight from the data on its own. So that's why something like clustering is a good application in that area in unsupervised learning. Do you understand? So those algorithms now, like these algorithms are for supervised learning. For unsupervised learning, we'll have to use things like k-means, clustering, and hierarchical clustering. But I just didn't mention it here because it's more is out of scope for this lecture.
Okay, I think I understand. Thanks.
Okay. Yes, Jonas. Jonas. Elma.
Hi, hello. I was just wondering, there's my camera.
Yes.
I was just wondering, would you be introducing also the role of data scientist, as we introduced the data engineer, which is important role in the data preparation. But in terms of machine learning, algorithms, and selection, I think data scientist role, and for my colleagues to understand
Okay.
this role, also DG talks about this role in our staff meetings.
Yes.
It would be good as part of one of these trainings to understand and maybe touch base a bit what Hugging Face and how many algorithms it has.
Okay.
And I would like to know what are the latest platforms that you know that facilitate the selection of the algorithms. I know about Dataiku, Microsoft, but maybe there are some other platforms that would facilitate or give us kind of like a library of the algorithms, and when they are the most searched from the education, or maybe there are universities working on such platforms. So it would be good to know what's there that we don't know. We know about the private platforms facilitating selection of modules, but I don't know anything about universities or such platforms. Thank you.
Okay. F- the first question, the role of data scientist, I will answer it. The other question, I feel like that is a bit out of scope, but I may just touch briefly on it, but is a bit out of scope. But basically, Hugging Face is a site where you can use publicly available machine learning models depending on your particular task at hand. So that's what is used for. Should you use it? Should you use it? It depends on the scenario. You understand? There are scenarios whereby it's beneficial to build the model from scratch for your use in your organization, maybe because of data privacy and all that kind of stuff. And there are scenarios whereby it's better to leverage on publicly available trained data already, maybe because of resources and stuff. So for example, to build a large language model now, well, okay, sorry, WTO may have the resources to do that, but is it a priority?
I wanted to say that Hugging Face has 1 million models. So
Yeah.
for my colleagues to understand the complexity of selecting the models, that's
Yeah.
why data scientist role has been introduced and is very popular right now in the world. The data scientists, they're trying to, at least in their organization or company perspective, figure out which models would be the best. And it's still ongoing because
still
there's
ongoing, yes.
every day new models being published. So it's really not easy an easy job to select the best model and keep it. I would say the best, and keep up on top of that model, because there's every day a new model. Anyway,
Yeah.
that's why this role is important, and we have really limited resources. So we might have data scientists only working on this, or we will work with the external companies who have this expertise. We don't know yet, but for sure we will not be developing our own models. That I don't see WTO. because there are already a million models on Hugging Face we can choose from.
Yes, but we don't know what those models were trained on. You know, they were not trained on WTO data, so the data might not be relevant to WTO. You
Yes.
understand? Yes. So
We will train the existing models on WTO data. That's certain. But I don't think we'll be creating our own models. We don't have a job role for that in WTO. We don't have a data scientist
okay.
who would be working on creating the model. But however, we can use existing models and train them on WTO data. That's certain. That is a very good point. Yeah.
Yes. Yeah. So basically, the role of the data scientist basically is just someone that combines both technical expertise in machine learning and domain expertise also. So yeah, so this is why it's, you know, as an internally, you people have to really decide, like, because all of you all have domain expertise, which is very rare to find. You understand? It's actually rarer than getting someone in a machine learning expert. You understand? So it all depends. It could be a combination, but usually a data scientist should have domain expertise and technical expertise in machine learning. So it could be from using Hugging Face to building it from scratch. The individual must be able to do both. He or she must cut across, you understand, based on the scenario, because you don't want to have someone that is just limited, that can only use Hugging Face. You have to be able to use Hugging Face and also build them from scratch. You know, is important. Yes. Any other question? Okay, I think that is it. Dr. Ike, is there closing remarks or anything? I don't.
Yes, I want to say thank you so much for this fantastic presentation, and I want to thank the participants for your engagement this morning. It's been a wonderful session, and this is a continuing conversation. If you have any questions, please feel free to email us at any time, and we're more than happy to respond to your questions adequately. So once again, thank you so much on behalf of the staff of Invest Your Boat. I want to say a big welcome and thank you. Thank you. Bye for now.
Thank you, everyone.
Thank you so much.
Bye.
Bye.
Thank you very much.
Bye.
Thank you.
Thank you.
Have a good day.
Bye-bye. Bye-bye.
Bye.